Good afternoon, everyone. So it is my pleasure to welcome Himadri to our center. So Himadri is presently an assistant professor at IIT Delhi, and before that he was PhD from JNU, and then he was a postdoc at HRIU, and then he was in JNU. Yeah. So Himadri actually works in a broad area of quantum information theory, entanglement, lots of application there. Today we will talk on transfer and protection of quantum information in hybrid systems. And today he will be here, so if you have any student want to talk with him after lunch, you can.
Just unwind.
Is it on?
No, you have to unwind it and put it in your collar.
Yeah, sure.
There's a switch.
Hello.
Yes.
Is it too loud?
No, you have to put it in your collar.
Yeah. Can you hear me at the back? Okay. Yeah. Thank you everyone for coming, and thank you to Manik and Arshada for inviting me here. And so today what I'm going to talk about is transfer and protection of quantum information in hybrid systems. As Manik mentioned, I actually work on a lot of different things, mostly quantum dynamics and how information and entanglement behave like in dynamical systems. So in the last few years, what I've been working on is how you can take cavity QED systems, how you can solid state systems, and how do you understand how information flows from one point to the other. And with the ultimate aim as like if you want to build a quantum network, if you want to build a quantum computation device, how would you go about it? How would you write down the equations? How would you solve these equations? Okay, so that would be the basic idea of my talk. It would not necessarily be very fulfilling from a quantum information mathematical structure or something, but I'll just try to give you an idea like if someday you were to think about how I can take my equations and think of a platform to apply it on, what are the platforms that are available, what kind of experiments we can do, and what are the theoretical tools you have at your disposal to study these systems. Okay, so this is what the rough background of my talk would be about. So one important thing is I'll start my talk with how did some aspects of quantum optics lead to what we call these days as hybrid quantum systems. Okay, so the first instance where you really need to quantize the electromagnetic field is when you need to study spontaneous emission, right? So this was the first time in Weisskopf and Wigner, they thought like if you have an excited atom, how does this excited atom spontaneously lose its excitation? And that comes through the theory of spontaneous emission. It interacts with the vacuum fields and loses its excitation. It's a Lorentzian around the transition center, and there is something small amount of Lamb shift. And this was the first theoretical model in which you needed to actually quantize the optical field to study the phenomenon. But in fact, you can do better. This was Purcell. Purcell said that you can have these exponential decays, but you can put this entire atom instead of interacting with free space vacuum modes, you can put them inside a cavity, and this cavity will select certain kind of modes and it will increase the density of states of those particular modes. And you can show that spontaneous emission in those particular modes will be greatly enhanced. Okay? But this is not all that you can do. James Cummings came up with an interesting idea. They said that you can put an atom inside a cavity not just to study how excitations decay or how spontaneous emission is. If you actually couple them very strongly, you can see how information or excitations flow from the atom to the cavity and back to the atom. So you have something known as Rabi oscillations. So you can have, like if you put an excitation or a photon inside, this photon will be absorbed by the atom will actually then give it back after some time. There will be a periodic transfer of excitations or information inside the system. So this was the so-called strong coupling regime. So you can have regimes in which excitations are completely lost. In another regime, you can have excitations which are coherently exchanged. So if you can think about, these are the first instances where you can understand how some small part of a qubit or something that a photon carries can effectively be transferred to some solid state or atomic system. Right? It lays the foundation for that. So this is the first instance of coherent transfer of information between two different quantum objects in some sense. And all of these were actually beautifully shown by Serge Haroche in his experiments, where he actually placed these huge Rydberg atoms inside high quality cavities, and he experimentally observed these kind of Rabi oscillations. So this is the population of the atom excited in ground state, and you can see that it actually fluctuates with the photon number increasing whenever the excitations go up and down. Okay, he won the Nobel Prize for this, I think, in 2006 or something, and this, in some sense, gave rise to the field what is known as cavity electrodynamics. And cavity electrodynamics at this point plays one of the fundamental role in building quantum computation and quantum protocols and other communication devices. Okay, and that's the aim that will start from cavity QED, how we go to hybrid systems and so forth. Okay, so the next step is, these are like some of the recent, you can say, state of the art. This is the Misha Lukin group in Harvard. Here you can see an instance of where he has an atom trapped in a photonic crystal. This is the Rauschenmodel group in Berlin. There's a rubidium atom trapped in what's known as a whispering gallery mode. And these are simple instances of how you can have like extremely highly engineered systems of an atom sitting inside a cavity. But the interesting thing is,
when you talk of real atoms,
yeah.
is it very different from what Haroche did?
No,
It's the same.
It's the same.
Maybe rubidium 85 was.
Yeah, yeah. So here now you have like these photonic crystals with particular, more engineered photonic systems which can interact with this.
So the atom is kept at rest somehow inside the cavity.
Yes, it's that. So you can, there are also instances where a stream of atoms actually flows through the cavities. And this is like there's a famous person, Jeff Kimball, I think. He uses these stream of atoms which flow through the cavity as.
But when you have the Doppler diagram.
Yeah, you have to account for those things. But the interesting thing is, you actually don't need real atoms anymore, or you actually don't even, you can engineer your resonators, right? So you can actually have a quantum dot that's behaving like a two-level system, that's your qubit. You can actually have a superconducting circuit where your some superconducting device is cooled and you use an LC oscillator and you really cool it down and quantize some aspect of it to create two levels. Right? You can have the right current flowing and left current flowing, or you can create a harmonic oscillator with some and harmonicity between them to create two levels. We'll discuss briefly upon that. You can have optomechanical resonators which are interacting with some two-level systems again. So the entire realm of what we traditionally call as light-matter interaction does not necessarily involve real light or real matter. These are artificially engineered systems, but the beauty is you can take a very similar set of theoretical understanding to even study these systems. Okay. So what do I mean by a hybrid quantum system? Okay. So a hybrid quantum system is one in which, say, I have something that's, say, a processor. What is a processor? Processor for me is, say, just a single qubit, or say 2 qubits in this instance. So in these 2 qubits, I can entangle them with some gate operation. I can perform some small computation task or something like that. So this is where the processing takes place. So ideally, we would like to reach thousands of logical qubits, which will allow us to do proper tasks. But you can have a processing unit that looks like these superconducting. They are static. We're not sure what kind of coherence they have, that they are static devices. And you can think that they are connected to some solid state system out here, which actually acts as a memory. Why do I call it a memory? You can actually choose something that has, say, very high coherence, that's very protected from the external environment. And then you can couple all of them with some kind of a resonator that allows information that is processed here to actually go to this memory and you can store it here, and you can again bring it back here. Okay, so you have different elements that are all put together, and you want some kind of a collective advantage that maybe each of the component don't necessarily provide you, right? So, for example, in the qubitting one, manipulation of the qubits is much easier, so I want to do it here compared to the solid state. But in solid state, I know that the qubits themselves are very stable. So as soon as the processing is done, I can transfer this information and want to keep it in the memory. And at some point, I want to bring it back and do some other protocol. So yeah.
When you say transfer information, are you like saying like you will decode it from the superconducting?
No, so you can think of it like so think about how in the traditional light you can think about Rabi oscillations. Right? So in Rabi oscillations you have some photonic feedback oscillation. So in here the resonator can be thought of carrying those kind of optical excitations around them and storing it there. So supposing if you have some incoming excitation, how is that stored inside the ensemble, and at some day you can actually leak the cavity and release it and take it out. And then you can send this information directly to some qubit, do some manipulation, and
How
then
do I
read the output.
visualize this?
So
In the
this-
quantum state.
Yeah, so think about if I, like from a theory point of view, you can define, say, the input state as a superposition of a single photon and a two photon state, or something like that. And then this information is then transferred to the qubits. It does an operation. There's an output. Take this output along the microwave resonator and put it back to the theoretical ensemble. So for you, as a theoretical physicist, what we are trying to understand is how would the entire dynamics play out? Like how would you have a two-level system? How is that talking to this system? As soon as you have a platform and you can get all the interactions correct, then you can write down the mathematical structure and try to solve it and predict what would be the fidelity with which this information will be transferred from the first to the second and so on.
So how do I model this transfer? Like quantum channel, how do I model this transfer?
Yeah, I'll show you. So you can actually just use simple James Cummings model as the base model. And what people ideally do is, supposing you're working with superconducting circuits, you look at what the effective interaction strengths are and map them to some Travis Cummings model or something. Okay. So what are some of the users? Like, so this is one picture where you have a qubit and this is an NV center that is here, and they are all connected by some micro a superconducting resonator. And these are often used as so-called quantum memories. You can also have something known as optomechanical transducers, where you have an optical cavity and you have an optical cavity and a membrane which is vibrating, and they are all coupled to a superconducting qubit. And what this does is this actually transports optical wavelengths into microwave wavelengths, right? So they can convert between optical and microwave frequencies. And this is another part you can take while building a quantum network. You can have other things, so you can have information processing. In this case, you can see there is a superconducting circuit and a magnon, which is inside a microwave cavity. You can also have waveguide mediated entanglement. You can have two qubits which are far apart, and there is some plasmonic waveguide that is creating an effective interaction and creating entanglement. So the idea is you can bring two different objects which look very different separately. You wouldn't really know whether they work in the same parameter regime or not, but you can try to bring different elements together and fit them and try to get some advantage which you would not actually get working just independently with them. Okay, and this in some sense then you can take back and make it a part of a larger quantum network. Okay, so a lot of the hybrid systems are based on, so you can have, say, rare earth spin ensemble, you can have ensemble of ultra atoms. You can have Minkowski modes in some of the qubits, like superconducting qubits. You can have nitrogen vacancy centers. There are a lot of different platforms that people have typically worked with. Okay, so yeah, so the next part is I'll try to basically motivate how would you go about trying to solve these systems. Right? So the simplest way, let's go back in history and start with the say simple James Cummings Hamiltonian. Okay? So in the James Cummings Hamiltonian, you simply say how a two-level system interacts with say light. Right? So you can have a single frequency. So what are the different terms? This first term is basically the energy term of the atomic spin system, right? you have the excited and the ground state. So just take the energy of that. This is the bare energy. Next is you can have the photon energy. So these are the pop state numbers or the pop numbers. So they basically count how many photons you have inside the thing. The next part is basically the spin photon coupling, or this G term. This is the rate at which. So these are energy conserving terms. So this coupling is this is the rate at which if a photon is annihilated, what is the excitation that is created, and vice versa. If a atom de-excites, what is the photon that's created and what's the rate at which that's happening. And this G basically says whether you're working the strong coupling regime where you get gravity oscillations, or if this G is actually very weak, you can study something like spontaneous emission. And then you can have external drive. So you can drive the system coherently with some external laser beam. And this, in some sense, just forms a simple picture of how a simple system would work with light. Right? So if you just look at a very simple solution of a Hamiltonian like this, you get something known as the dress states. Right? So if I take this Hamiltonian, so think about it, the coupling out here is actually energy conserving, right? Whenever a photon is created, the atom has to de-excite. So the total number of excitation in the system is always conserved. So if the total number of excitation is always conserved, this Hamiltonian can be written in terms of each blocks. For each block, the total number of excitation is, say, n. And you can actually diagonalize just one particular block and you'll have the eigenstates of all the blocks in between. Right? That makes sense. So since it's conserved, you can't actually, unless there's an external energy coming in, you can't jump from one energy block to the other block because the energy is conserved in each. But if you just take this block and you like diagonalize it, you'll see you'll get a pair of these entangled states, and the separation split between these two is basically dependent on G. So as the coupling increases, you get this separation between two. Otherwise, they would have been energetically the same. You get the splitting, and you create these two entangled states. One important feature is, so one important feature here is these are not really harmonic in nature. They're all split with different energies, right? So if I were to drive the system in such a way that I only access these two levels, this excitation is completely inaccessible to anything else. The system can't actually coherently jump anywhere else. Or even if it does, it will do it with a very, very low probability, right? So this is your simplest description of how you can actually, create a qubit, like in a theoretical sense. You bring a light matter kind of interaction and you create a artificial, not artificial, in the sense real and harmonic structure. And if your system is only exciting, only talking to this particular transition, then all the other transitions are forbidden. So these are known as the single photon regimes. This is called photon blockade. So if you look at the G2 function, it really dips out here and the polaritons actually peak. So polaritonic peaks are basically nothing but these energy levels. So they are dress states of light and matter. So the state at these state at this point are basically entangled between the atom and the light, right? They don't have a different description of the role. So they are just a single quantum entity. So these are so-called polaritons. And you can see like all other transitions will actually be blocked, and these transitions will actually just have like high frequency of taking place. So in the simplest sense, what I'm trying to say is if you start with a simple light matter interaction Hamiltonian, you diagonalize it and you look at these energy eigenstates which are entangled. And if you just address one of them, you see you already get a notion of what the qubit is. In fact, you can also try to excite and control and take the system to some other specific level if you're interested to create some other structure. So in an atom, you can have multiple levels, but if this anharmonic structure exists, then you can actually drive your system in such a way that you can attract two particular levels to behave as qubits. Okay, so from single atoms, we want to like to go to a many atoms picture because many atoms is a crucial part of building hybrid systems. So in hybrid systems, we have the qubit, we also have this ensemble. So we have to look at how you would go around looking at the ensemble and why you need to study ensembles. So one reason when you look at single spins and many spins is you can see that for n max greater than 1, the energy levels are different than a single spin. So even though this first one actually looks very similar, you can actually get different splittings as you go to higher energy levels. Okay? And one thing is, if n actually now becomes really, really large, this entire splitting, if you go to large n, actually becomes very harmonic in nature. So the unharmonic nature, which was actually giving you the qubit, that does not hold anymore, but you end up with a harmonic subset. The states tend to behave more like a classical harmonic oscillator rather than behaving like a qubit-like system. So you can say that by going to a large n system, we have actually traded off some of the non-classicality that we had, that entangled state and the benefit that we got. But so what are the other kind of benefits that you can possibly get? One important benefit that you immediately get is you reach this strong coupling regime much, much more easily. So why is this useful? I can now work with some system which actually does not really interact well with each other, not with light. But if they are in an ensemble, I can get a square root and amplification on the coupling strength. So even though themselves they don't actually couple with any of these light because they are so isolated and free, as a group, as a bunch, they highly interact with the thing. So you can work even in the very small G limit, but simply by increasing this number of n, you can go to the high coupling level. So this is one advantage you get. But of course, the disadvantage is you throw away a lot of the non-classicality that you got in the single atom light region. Okay. So again, yeah, if you go to this large collective thing, you tend to see a lot of collective features that come out when you do work with large ensembles. So just to recap from single atom to an ensemble, in ensembles you get collective behavior which can be used for quantum memories, whereas in single spin you have non-classical physics, entanglement, you have single photon sources. But in hybrid systems, what we want to do is we want to work in a regime where we can try to bring these two together. So that is one of the main aim of our talk. Can we work in a regime in which, say, you have, say, 100 spins, a smaller number, where maybe the entanglement and the non-classicality can be preserved, but we also get a lot of the collective behavior. Okay, so this will allow us to manipulate information, use non-classical features, but at the same time, not necessarily give up on some of them. So try to bridge these two particular points. Okay. So again, we can start with the Davis-Cummings Hamiltonian. So in the Davis-Cummings Hamiltonian, again, we have the same part. Only difference is we call it Davis because this has now become N instead of a single atom, but you can now have many atoms. And you can have a distribution of the coupling across all these different atoms, and again, you can have a driving term. Okay. But now, supposing if this entire system is a realistic physical system where you can do some kind of quantum information task, then in general these systems can be open, right? They're not necessarily closed systems. So instead of just working with the Hamiltonian, I actually write down the Lindblad equation solutions of the system. Okay, so and you can see that this actually increases the Hilbert space like massively, like as n increases, your Hilbert space will increase exponentially. So even if you just have n qubits, your Hilbert space goes as 2 to the power n. If you are working with density matrices, they are roughly going as 4 to the power n. Okay. So in the large n limit, when the system is extremely large, one thing that people immediately do is they write down semi-classical equations. And why do they write down semi-classical equations? Is because of what we discussed earlier. Your system tends to become more harmonic, so you lose some of the non-classicality. So semi-classical physics sometimes already gives you the correct dynamics. But in semi-classical equations, one of the first assumptions you make is all your expectation values, you can actually decouple the photonic and the emitter part. So the light part and the matter part, you can just simply decouple them. And then you can independently just solve a small closed set of equations and get what the dynamics is. But what would you have, what did we do in the single photon case, in the single atom case? In the single atom case, we exactly diagonalize this Hamiltonian. And when you exactly diagonalize this Hamiltonian, you get the full mechanics. Like I could write down what the entangled states of the energy levels were, what were the partitions, what was the anharmonic nature, and I could exactly see what it is. But if there is no correlations here, none of the states actually end up being entangled, right? I'm throwing it away. I'm assuming that you don't need it anymore. So, but now we want to work in a mesoscopic regime. In the mesoscopic regime, how would we go about it? One way is there are a lot of methods in which you can have a restricted system. So you can say you have low excitation such that you only consider first few energy levels. You can use something like effective Hamiltonians. If you assume your spin ensembles are really small, you can use something called quantum trajectories. You can use permutation symmetry. If all your spins are identical, you can just assume that there is an overarching symmetry about the spins and throw away a lot of the Hilbert space. But all of these have some kind of restrictions. So in our like in most of the work that we've done, what we've tried to do is we've tried to use a variational renormalization method. So this is something I'll not touch upon in a lot of detail, but if any of you are interested, I can have a chat with you later. So here, but why I will still show this is because there's a very beautiful quantum information related thing connected to this. So what does variation renormalization methods do and how it can be used in this context is, so in general, if you have a many-body quantum state, right? So if you have a quantum state with multiple parties, it could be a strongly correlated system, it could be any generic system, and these usually occupy a large unit space. But if you know for some reason that this state is actually weakly entangled, and it so happens for ground states of a lot of 1D models, among other things, even in some 2D model. If you know your large thing is weakly entangled, you know from Schmidt decomposition principle that you actually don't use all the eigenspace, right? Like your Schmidt rank is not actually that high. Because if your Schmidt rank is really high and they're all equal, it means your state is highly entangled. So if your Schmidt rank is actually much lower, you're actually not using a lot of the Hilbert space. So can you map this entire Hilbert space to a much more smaller space? And that is the underlying area. So even if your n is very large, but simply by the fact that your system is actually not really entangled, you can actually map this entire system to a much smaller corner. And in this corner, if the size is amenable to your solution, you can use your classical computer or your HPC to actually solve this problem. And this is the underlying principle behind all density matrix denormalization group, MPS, tensor network methods, and this is used right from solid state, strongly condensed matter physics to even high energy physics with the same underlying principle. But remember, in our case, the system was not unitary dynamics. We actually have open system dynamics. We actually solving the Ringler. So we want to map this to the language of density operators and open dynamics.
Yes. So this three method that you showed, these are mainly to find the ground state, or am I wrong? Ground
No,
state
you can even find the
dynamics as you can do.
So EBB is
TEP.
service. Okay, so how do you map this to the language of density operators and open dynamics? So in this, you actually work in a much larger Hilbert space, but you have to understand a lot of this physics is independent of the physical system. You can take it to the language of linear algebra and matrices. So you can map all your density operators to a larger Hilbert space and vectorize them. And then you can still come up with a similar kind of a connection for weakly correlated states, because now the kind of Schmidt decompositions that you write are not necessarily physical states and does not necessarily convey entanglement, but it does convey some kind of a correlation. And for weakly correlated states, even for open dynamics, you can map this entire system to a much smaller Hilbert space. And this is one of the techniques that we use to study how you can actually have components of a hybrid system and you can couple them. And then if you start with some information going into one part, you can actually exactly evolve the system, and with time you can see where this excitation is Okay, so let us look at okay. So let us look at some examples of the kind of work that we did. Okay, so the first thing we did was we tried studying how information can be. Yeah, yeah. So I just listen.
So I'm saying, so this is a mathematical description that how the total n number of states are entangled. Since it is a weakly entangled, actually we can do some mathematics that it is in the this subspace. This is the highly entangled.
Yeah.
But if I use these things in physical, then I have to do some operations on that and make that entanglement shifted into that.
No, 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 no. So think about it. All you have to do is just change the basis, right? So supposing think about Schmidt decomposition. So Schmidt decomposition, supposing is there a blackboard? I can use that. Right? So if I have psi is equal to so what would this be? Okay. So this I've written 1 by square root d, where d is the dimension of say one of the smaller systems. And so one of the smallest dimensions is d, and the larger dimension will also be mapped to d. Rest of that will be 0. So in this case, all the eigenvalues are finite. I have to take them, right? But then, and this is also in some sense of Maxwellian dimension. But in principle, I can have say lambda I, and say lambda 1 is actually say some number a, and lambda 2 is some number b, and all the other lambda is a 0. So this system effectively lives in just two bases because rest is null space. Yeah. So if I have a transformation that just maps the entire system to that smaller space, rest of it is null space, so I actually don't need it. So idea is I just need a singularity transformation that takes me from the present basis to this basis where this thing is. So you just do singular value decomposition, find the thing and rotate everything to that state. You'll see everything is zero. It is a much more calculate all your observables in that basis, everything becomes true, right? So that's the central idea. So as you evolve the system, more entanglement will start growing. This system will start growing larger. But for certain systems where you know that this entanglement or the correlation will surely not go beyond a certain point, you can track the dynamics right up to that point. That's the idea. Okay. So you can actually just do this. Like supposing you're solving it and mapping it, just count what are the total values of lambda is. If they all add up to 1, that means you've taken enough bases. Right? If as soon as they don't add up to 1, take the square of it. If the square of it doesn't add up to 1, that means your approximation is not correct. That's the idea. So let's take some examples of where we have worked with this system. So one first thing is let's consider something called a spectral frequency comb. So spectral frequency comb is sounds a bit strange, but it's actually not. Think I have a lot of these emitters and they all have some specific frequencies. Okay, so it's like a comb-like structure of frequencies. And this is used a lot even in semi-classical quantum memory type operations, right? The group in Geneva, Nicola Giza uses this effectively. You use for a lot of different purposes. They apparently gave a very nice platform in which you can store Gaussian states that are coming in and stuff. But we want non-classical stuff. We want quantum information. But this is our starting point. One way to think about it is, yeah, we want to collect it, but non-classical features. We are not interested in just saving a Gaussian state. So you can actually map this in a superconducting circuit. So this is by Johannes Fink's group in Austria, and they actually have mapped for 5 such discrete frequencies on a superconducting circuit. We are working with them on trying to realize this and see what the results are. So think about it now, if this is a part of my hybrid circuit, and I have some quantum processor somewhere else, and that quantum processor say sends me a signal. First instances say it sends a coherent state, and at some later time I want the coherent state to actually come out. And of course, what this thing will do is this thing will store the entire coherent state in its ensemble, and after some periodic time will release the coherent state. And this time, what I'm trying to do is say, ideally, I'm assuming is the time I need to actually keep this information. But it will not be the same coherent state. There will be some rotation, the size will change, the fidelity will not be the same. But this is fine. Can I also do that to some random superposition? Can I have a superposition of say 0 and 1 vacuum and a single photon, or 1 and 2, and also get something here? Then this is actually really useful to me. This actually carries some useful. I can import some quantum information in this qubit, and this qubit can actually come out and like I can use it for some transfer of some information. In fact, I can also use a CAT state. I can have macroscopic states that are in actually superposition, and I can check how well the superposition is actually spread. Okay, so this is what we really do. We actually write down the Tavis-Cummings Hamiltonian, where this is the input field that's coming from one side, and this is my entire spin ensemble or a hybrid system, and this is what the output field looks like. And all of this, I start with some initial state, I apply some kind of a renormalization group method, and we computationally try to see what other states that can be created. Okay, and then once we have this, we look at this is the time, and this is the average photon number that is coming out. So just for ease of understanding, like these are different photon numbers for different states that we've considered. And in this case, we basically put the Wigner function, because matching the photon number does not actually tell you anything, right? Like you can have a coherent state as well as a superposition state as well as a squeeze state, all with the same photon number, but you don't know whether these states are entangled or whether these states are different or not. So we actually plot the Wigner function, and then we also plot the fidelity here, right? And you can see that for the coherent state, you can see that there is a parity shift in the first revival, but in the second revival, you actually get back to the state with considerably close fidelity, right? So you can see it's actually quite high, not really exactly equal to 1, but it's quite high, even for a Schrodinger cat state. Right? So these Schrodinger cat state are even parity states, so the parity doesn't change. For the other, the parity shifts in the first revival. In the second revival, you actually get back the entire state. Okay? Yeah, so this is the Wigner function at time t, parity transformation first revival, and original fidelity at t equal to 2. But you can actually engineer your ensemble in such a way so that you can actually improve this fidelity. So if this is the coupling strength in each of the comb, so this over here decides what the coupling strength is. The coupling strength is different. There's some kind of an inhomogeneity in the system. They don't identically couple to the ring. And if you adjust this coupling, like if these are the different strengths that you get, then you'll find that there is an optimal coupling strength, right, for which the fidelity is actually high. So look at the orange line out here, or the reddish orange line. And for this, you can see if you compare the fidelity at the fourth revival, you can see you get very, very high fidelity.
Even at the fidelity for the arbitrary superposition or the cats?
I think this is for the arbitrary superposition.
Arbitrary
Is- Sorry, I didn't note it down.
But in the last slide, I saw that for some reason, if you go to the last slide, it seems the cat state performs better compared to the arbitrary superposition. Is it, or it is?
No, I think it is the same. So this is high.
For the second-
It's just in the parity state, it is just the opposite.
It is the
So in this case, since it's even parity, it has high fidelity. But I think it's for the cat state this figure. Okay, so yeah, you can just play around with the way you couple this system, and you can see that you get high fidelity. And so why is this the reason? The reason is actually quite striking. What you actually see is, if you calculate the energy differences, so you calculate the enharmonicity of the eigen levels, you can see as you tend to change the system with this different coupling strengths, the point at which all the levels actually become similar or equispaced, that's where the fidelity tends to be higher. So even though the system is behaving non-classically, the way it's structured or the way the fidelity is done best is both of them become identical oscillators in some sense, because they are not, they are, even though they are enharmonic, they are tending to be more harmonic. And if you can tend to make them more harmonic in nature, then they tend to actually reproduce the state much better. So this is still expected, right? Like if I have two classical objects and two classical oscillators, they will perfectly just keep giving information one to the other, right? So you need to have a non-classical distribution of slides, but you need to arrange it in such a way that your anharmonicity is as least as possible, and this still gives you a sufficiently good storage or mode to keep the transfer, keep the any quantum information that's coming. It could just be 2-qubit superposition between 0 and 1. It could be superposition between two macroscopic states, but it will still do it with very high fidelity. Okay. So one reason, like this is something I didn't touch upon. It was a previous work that we had, but I didn't touch upon that. One reason people use these atomic frequency combs is atomic frequency combs actually allow you to mitigate a lot of the effects that come due to losses in the system. Right? So there's a different paper in which we discuss how this actually takes place. But in this case, we were just using the atomic frequency comb as efficiently as possible to allow for maximum fidelity. Again, this is in some sense mitigating the losses in the system. Okay, so the second example is a more recent example we looked at. So one of the major disadvantages of working with spin ensembles is if you put a lot of the spin ensembles together and if they're actually not homogeneous. So if they're all homogeneous, they'll behave like one single giant spin, right? But if they're not homogeneous, this inhomogeneity in itself can create losses in the system. So this inhomogeneous broadening, simply by the fact that these systems are not identical, when if there's any information that comes into it, when it's actually stored inside the ensemble and it comes out, it will not come out as perfectly as if it were homogeneous. This is understandable. If there is a classical light, if it's homogeneous, it's like one classical oscillator, light comes in, light perfectly goes out. But if it's inhomogeneous, the information will tend to get lost in the large diverse Hilbert space of the system. It will try to leak into other kind of transitions from which it can't recover or interfere back in time to give you the exact oscillations back, right? So inhomogeneity tends to throw information across a lot of different corners of the Hilbert space, and sometimes, and it doesn't have enough time to all come back together and interfere possibly, right? So you can calculate that an effective decoherence rate. So this is one paper that does it, but this is much older formula. You can see that your effective decoherence is kappa, which is the loss of the photons, and you get another term which is dependent on how the density of the spins is distributed in space. So if rho is the density of spins at some frequency omega s, and this is what the equation looks like. So look at this function properly. So what does this actually say? This is that it's not dependent on the distribution of the spins everywhere, but it is only dependent on the distribution of spins at two particular locations in the thing. So actually it's also there in the slide. So if this is some omega naught, and you have huge number of spins or emitters, and they all have a frequency distribution around this particular point, all it says is it depends on the density at two particular points where it's minus omega and plus omega. And these are the points, if you remember the structure that we had, is where the polaritonic peaks were forming, right? This is like when you split the energy into the entangled states. These are the points at which you're getting the polaritonic peaks. And the density at those places are actually what matters. So one quick way what you can do is, yeah, so if these are your polaritonic peaks, the density at this particular way actually matters. So if I increase the coupling strength, this omega out here, capital omega, this is the collective coupling strength. Then the polar electronic peaks will just simply move away, right? And you can see that the density will actually significantly drop. So for the same ensemble, if I can somehow manage to couple them strongly, I can actually move the polar electronic peaks away, and the density, which was some finite large number, actually becomes a very, very small number here. So this is something that is called cavity protection effect. Okay. So if you have a large ensemble where it's interacting with the cavity, it can be a micro resonator. So it applies to all other hybrid systems too. Simply by making sure that you enhance the cavity coupling in some way, you can actually get reduce the density at these 2 points and greatly reduce this number. Another thing that you can do is you can do spectral hole burning. So you can take 2 lasers and just burn out all the atoms which are at this point. Right? So there's a row of omega is out here. Just burn 2 holes here, so that no emitters are there at those particular frequencies. And this entire term actually can go to 0, and then all your decoherence between homogeneities. And this can actually be shown even experimentally. Right? So there are different ways. But then imagine like burning 2 holes in a spin distribution where you're also trying to do quantum information, trying to do some quantum protocol. So this is a very, very crazy thing to do, right? You can't really do it.
And Himadri, the second thing, how does your this coherence due to homogeneity, the second term, compare with the first term, that is the intrinsic decoherence?
Yeah, so that could be material dependent.
That is material.
So if you can have also dependent on like you can really have a very high quality cavity with this entire kappa is zero.
Where the kappa is negative.
Yeah.
So all the decoherence is due
Purely
to
inclusion.
so that you have to control.
Yeah. Then this becomes your like biggest enemy. So ideally, all experimentalists will try to improve kappa first, and then try to tackle this. Yeah. So in this case, like what they do is you shine 2 lasers, but this laser will then also start affecting other parts of your entire system. And even in this case, there is only a limit up to which you can increase the strong coupling, right? Like it's not very easy. If I give you an ensemble with some numbers and suddenly say, okay, this is the number you have, why don't you increase it by a factor of something and get a huge number? Like it's not that simple. So one way what we thought about or how it can be looked at is, supposing you have a parametric driving, like you have a squeeze-like driving or a 2-photon driving in the system. Now let's look at the simple Tyrus-Cummings Hamiltonian that we had earlier. But now I'm driving the system with a parametric drive, right? Instead of so this is a parametric, so it's a 2-photon drive instead of simple coherent drive. And what you can see is in the squeezed wave, look at the coupling term here. So the coupling term has this exponential ER term. So by controlling this with the parametric drive, you can actually increase the coupling strength. And this allows you to, if your coupling strength was some GK, it allows you to effectively go to some coupling strength GK, e to the power R. And this actually moves your polar electronic peaks further away, and you can achieve the cavity coupling. So this entire thing you can actually derive analytically and show that it should ideally work. But then again, we go to a mesoscopic, we apply it both to the large L limit where you have semi-classical results, and we also apply it to the system where you have mesoscopic system, and you can see that you can compare the two. So you can see that by increasing the squeezing parameter, you can actually increase and get back the Rabi oscillations which were actually damping earlier. So the red one you can see is damping very quickly. With the blue and the black one you can see you can recover. Yeah. So one complaint you can have is, are you sure how easy it's to get these squeezing parameters? So yeah, I'll behave like a theoretical physicist and say, yeah, it should not be that difficult. But I'm sure people will not agree. But in principle, if you can get there, if you can squeeze the light well enough, you should be able to actually achieve. And this is non-invasive, right? Like I'm not shining any lasers inside. I'm driving it externally with some squeeze light. I'm not re-engineering any system externally. But yeah, so you can see that the rate of decay decreases with increased squeezing for different widths. You can also actually look at the Wigner function. So I think if this is the initial light, and this is the light you would have got without the squeezing. So you can see that this is what if your initial light was, it just becomes a simple blob out. So you've lost all phase information. But if you squeeze it, using squeeze light, you can effectively increase the thing and you can see that you get back some kind of phase coherence. Okay. And these were again done in, say, in the mesoscopic regime. I think this was again taking it to 2 or 3 arbitrary superpositions of initial states to see what the V2 function is. Okay, so this is the take-home message. Like what I was trying to see is how we got from initial light-matter interaction to hybrid quantum systems as we know it today. And hybrid quantum systems play a key role in design of all quantum computation devices. So if you think about superconducting circuits, trapped ions, NV centers, all of these actually use light-matter interaction in some form or the other. And in some sense, it's essential to know how best you can study the dynamics of the systems, how best you can understand how information entanglement is flowing among the systems, how can you create more entanglement, or how can you mitigate losses that come due to different parts in the system. Okay, and so that is what we are aiming for is predicting parameters that will allow efficient memory operations, will allow for sharper communication. And also one thing that we are working on is using similar paradigm, how can you study error correction using collective states in these light-matter systems. Okay, so yeah, I just flashed people in my group at IIT Bombay. They are my 4 PhD students, and these are all masters and BTP students. So Siddharth Tiwari was a undergraduate student who is now at Berkeley, who actually worked on the second part of the research. And so I just flash his name, and yeah, thank you so much.
Two questions if you have.
Can you once again tell me what it is the hybrid?
So the reason we call it hybrid is, you actually don't need to necessarily call it hybrid, but what people mean by hybrid is you would have they are essentially very different systems which ideally you would have studied differently. So a superconducting qubit, you would ideally take it alone and just study what kind of gates you can do or how you can entangle them or what you can create. But in hybrid systems, you essentially are trying to push it to a regime where it can talk to some other system. And this other system could be very different. Say it could be a magnon or a Euclidean iron garnet sphere. And this qubit, which operates in a different regime, is somehow trying to couple to this and pass information along this. And then they are all put in some copper box, which acts as a wavelength. So there are all different systems which are coming together, but you want some collective advantage. They all have different properties. Maybe one is not coherent, but the other is. One is easy to control, but the other is not. So they come together with different qualities and contribute for you to achieve some goal. So in that sense, that's why they are colliding.
Any more questions? But generally, storage of information in real time scale, how much time?
So different systems have different, I think, so people will give you a lot of numbers. So like from a purely experimental point of view, but there will be restrictions as to what kind of states they are. So I think Nikola and all, they can actually store it up to quite like 100 nanoseconds or even, no, in fact, using NV centers with nuclear spins, you can actually go very close to like seconds range or some fraction of seconds or something like that. But it's very difficult to manipulate and control those. So this Magnon paper was quite it has a good number.
Science.
So this was from Yale, I think, but yeah, this one is, so they had 100 nanoseconds here, but this is very first of the Magnon experiments. Yeah, but I think in NV centers, I think NV centers nuclear spins are the most stable for keeping.
That means cover it.
Yeah.
That side we cover it or something? Nuclear thing like this?
No, this I don't know. I think what they do is they actually attack the electronic spins and then try to find
Indirectly,
some.
indirectly.
Yeah. But I think it's not very easy to do.
Oh, yeah.
Because the nuclear spins are very stable.
Yeah,
If it were easy, I think we would have already had a negative. But I think it's
It's an indirect phenomenon.
yeah, indirect.
So this is something completely out of the air. Very good. But there is some excitement regarding something which is called time crystals.
Yeah.
So in such systems, has anybody thought of implementing a time crystal?
Paper cell.
You mean in these systems?
Yeah.
Yeah. In this system,
So there.
you mean not quantum? You mean in
Time crystals in cavity.
yeah.
Even,
People
and it's theoretical paper cell.
theoretical.
Yeah.
No, experimental, I'm not sure. So even experimental, I'm not sure. But
Theory
theory,
paper cell.
theory,
So the real cavity theory or your these
I
superconducting
think in
systems? Both.
both. So theory people, yeah, sometimes we tend to push the parameters to, and we assume that. So if someone asks me whether this parameter, I'll say yeah, superconducting people can come up with any parameter because they can tune it. But in principle, time crystal in cavity QED is a very strong.
If no more question, let us thanks Himadri for
Yeah. Thank you so much for coming. I'm not sure if today is a holiday, but yeah, thanks for attending.
It is not in the